Thank you for joining us at our third Des Moines S5 event. Our speaker tonight is Professor Daniel Alexander. Professor Alexander is a professor of mathematics and associate chair of mathematics at Drake University. He specializes in complex dynamics, which is one of the early manifestations of chaos theory. Professor Alexander has published 2 books on the subject, Early Days in Complex Analysis and History of Complex Dynamics from Schroeder to Fateau to Julia, as well as several articles and reviews. I hope to have the pleasure of studying real analysis with Professor Alexander next year. Please welcome Professor Daniel Alexander.
Thank you. Very gracious. So I kind of like to know who I'm talking to. So do you mind going around, like, just, since it's small enough, we can do that. He said something about me, so, you know, if you want to just maybe say a little bit about where you go to school, what you like, or something like that. Yeah, why don't you start, just so I know your names.
I'm Nathan. I go to Hoover and Central.
Okay.
Evan, I go to Valley.
Arjun, I go to Valley too.
Okay. Everybody, right?
My name's Ala. I'm well over.
Oh, are you his? Okay. Did I email you?
It's my email. Yeah.
Yeah, that's what I thought. Yeah. Okay. Yeah. Okay. Nobody's exempt.
Scott Easton, I'm Evan's dad.
Oh, okay.
Mike,
You're just here?
I took calculus.
Oh, good.
I'm Alexander Wayne. I work for the district and I'm writing an article on Moines side.
Oh, good. Okay. The West Moines School District? Yeah, okay, good. Okay. Good. We just went through introductions. I don't know if you want to introduce yourself, or both of you, or yeah.
Sure. My name is Keika, and my son is Arun. He's in middle school, and my other son is Arjun.
Oh, good. Okay, yeah. Well, I'm glad you all could come. I've had classes smaller than this, so I'm comfortable with small groups. So I guess before I start, when Gabriel sort of approached me about this, he said some of it was just to talk to how people get into STEM and some of the things that are available with STEM careers and things like that. And so I'll talk a little bit. I might worry some parents, if I talk about how I got into math, but I'm going to do it anyway. I was an English major in college. I was really good at math. I was good at math as a kid. I used to say I was really good, but I'd met too many kids that are really good. And I wasn't quite that good, but I was good, and I really enjoyed it. It was kind of my favorite thing. And then, but like when I went to school, I was kind of more interested in books and the world, and math seemed kind of like, it was all nice and tidy, and it seemed kind of like, not boring, because I always really liked it and thought it was really exciting, but it didn't seem to be kind of like the exciting stuff that was going on, which I was totally wrong about that, as we've come to learn, but that's a whole other story. But so I ended up trying a bunch of different majors. I ended up being an English major, and that actually was a great decision, because not only do I like books and things like that, but I learned a lot. I learned how to think in a way that's different than mathematicians think, which is good. I got some writing skills that I learned the hard way later, but I think the bedrock was sort of there in college. I'm not sure how well I realized it. And there's things I was exposed to that I wouldn't have been. I mean, books, ideas, all kinds of things. But what I didn't like about English is that, like, how could I tell somebody what a book meant? I wanted to teach. I always wanted to be a professor. Well, not always, but I wanted to be a professor when I was in college. But I mean, I couldn't tell someone, like, how would I know what a book meant to them? So it was like, I was saying, how can I stand in front of a class and tell them how they're supposed to interpret a book when it's just so open-ended? And it just seemed to me something I wasn't comfortable with, because I think what a lot of people do is when they read or think about things, they do it in their own way. And English professors have gotten around that today by talking about other things, but that's a whole different story. But I didn't know that then. And so I did a few different things. This was when I graduated from college. It was the mid-'70s, so the Vietnam War was just ending, and the 60s were kind of dying out and things like that. But I wanted to kind of explore life, and this is where I say maybe all the parents here may not like this, but I did things like I worked manual labor. I worked at a fish pier in Cape Cod, so I had an ocean view. My office was outside by the ocean. Most days that was good, but if it was cold and wet, it wasn't so good. I ended up smelling like fish pretty much the whole summer, so I didn't have like an active dating life or anything like that. I don't think. I blamed the fish on that. And so I did that for a year, and I liked it. And then I started to work in the restaurant business, which I really enjoyed, because it was, literally thinking on your feet, because you're on your feet all the time. You have to interact with people. And I think I learned a lot of good skills there. Among them, I'm never afraid in the classroom. I don't really teach, like I've never really taught in really dangerous situations, but like I figure if I can handle people in a restaurant or a bar, I can handle a group of students. I mean, they're much, much easier to deal with, you know, much better frame of mind. But again, that was something I realized that wasn't going to really sustain me. And so I went back to school to study journalism, because I really had an interest in writing. So a couple of years after I graduated from college, I went back to study journalism. And what I had to do was call people on the phone, interrupt their dinner, and I hated that. I discovered, like, when I was writing stories that it just, you know, I'd call them up, interrupt their dinner, and they, you know, I don't know, I felt like I was really intruding on their lives. So I said that wasn't for me either. So here I am in my mid-20s. I've already discarded 2 or 3 careers. And then I went, so I continued to bartend. I was bartending and managed this restaurant. And we got the first programmable cash register. And this might be hard to believe for some people here, that in the old days, people actually had to add, make change and things like that. It didn't read out on a piece of paper how much we were supposed to give back. And in fact, our cash register wasn't even looked. It was completely manual, and really you had no help at all. So you had to, you know, count your change and figure it out. And it was no big deal. But we got this first programmable cash register. And again, if you're of a certain age, you might remember these manuals that came in sort of a version of English which doesn't look like English at all. And you have no idea what's being said. And so we had this manual. And I think if Google had invented that, it would have been like a manual that somebody wrote in a different language and like put through a translator. So it made no sense. And so I really got into trying to figure out how it worked. It got kind of, in a good way, obsessive. I just like trial and error, and I reverse engineered it and figured out how to do these things, how to make reports. And it just seemed like a really interesting problem to solve. And then somebody said, you know, you're an English major, obviously it looks like you're good with computers, you should become a technical writer. So I said, okay, I'm going to go try that. So I went to a local school to learn technical writing. And this is already with a master's in journalism and then an undergraduate degree. And then they said, well, you have to take some computer science courses. And I said, well, okay, you know. And then they said, to do the computer science, you'll have to take some math courses. And again, I said, okay, I can do that. I used to be good at math. And I'd forgotten everything. I'd taken a calculus course, and I found my old notebook, and I had no idea who wrote it, even though clearly I wrote it at some point in my life. It was my handwriting. I'd forgotten what a logarithm was. I'd forgotten what trigonometry was. But I remembered my algebra really good. I think it was the algebra skills that sort of helped me figure out how to work that cash register. And it also helped me figure out when numbers didn't add up, when we did the daily reports, and there's like, you know, like $9.95 missing, I'd say, well, you know, the fish cost $9.95, so maybe somebody wrote it wrong. And so I kind of would figure out that using algebra in ways I didn't realize it. So gradually, I'd sort of built up these algebra skills on the job without knowing it. I went back to study computer science, and I just loved programming. I said, why bother writing the manuals? I can write the programs, and I really enjoyed that. And then, but the math, I kept taking more math courses, and that kept sinking, you know, it kept like getting more deeper in my soul, deeper in my head. And then all of a sudden I kind of realized, this is really what I want to do. And so one day I said, I'd gotten sick of writing programs. Like it used to be in the old days, you would write whatever language you'd use, the first thing you would write would be hello world or something like that. And so I did that, and it was maybe the 5th language, and I said, I'm sick of this. I love tutoring, I love working with math, I think I want to teach math. And so that was in my mid-20s. And so I decided to do that. Now, I was going to a commuter school in Boston, UMass Boston. I was working in the tutoring lab as a tutor, and all the students were saying, oh, you should be my teacher. You're so much clearer, you know. You're so much nicer than my teacher. I've learned that that's what tutors say to all the students now. And I think my students tell the tutors that same thing, you know, like, I wish you were my teacher, you know. He's so, you know, he's not very clear and everything. So I figured I was getting tired I believed the students that were telling me that. So I went to the chair of the math department as a student and said, I'd like to teach a math course. And he goes, well, you know, you need a master's degree. I said, but I have a master's degree. I went to journalism school. And he thought about it, looked out the window, and this was in Boston. It was overlooking the Boston Harbor. It's right, if you've ever been to the JFK Library in Boston, it's right next to that. And so he looked out this window, and it was a beautiful day, kind of like last week, nice and warm and sunny, and he goes, that'll work. And so he hired me on the basis of my journalism degree to teach math. And I thought that was just the best job in the world. And so gradually I did that, went to grad school, got my PhD. and that's sort of how I got here right now. My PhD was in the history of mathematics, and to me, I have this theory that anybody learning math, which is one of the most abstract things, has to apply it to the real world, or has to make sense of it in some way. And for me, it was the history. Like if I understood, you read these bizarre ideas in mathematics, I'd wonder, who thought this up? And so through the history, you start to learn how these really weird ideas come up, and they don't seem so weird anymore, they seem kind of natural. There's historical reasons for why it happened. There's questions people wanted to know about existing math or about the world. And so I find that a really fascinating way to look at mathematics is, okay, why did they do this? And how did this come to be? And I ended up studying the history of some modern mathematics, which, as Gabriel said, is called complex dynamics. And it's an early manifestation of chaos theory. I can talk about that later if you want. So anyway, that's how I got to here. And I think, so STEM careers, I think, are great. People think you're smart even if you're not. Like I remember when I went back to math, people said, you must be really smart. You know math, and it was kind of like, it felt good to hear people say that. And it's also, like I mentioned earlier, I didn't like teaching English because how can I say what's true about a book? But with math, I think I can say what's true. You can. And to me, that's a really satisfying thing. You know what you're doing is either right or, it can take a long time to figure it out, but eventually, in theory, maybe, you can figure out if it's right or wrong. The good questions are ones that take a long, long time to answer, like it can take weeks or months or years or lifetimes, so not for me so much, but some of the questions that are still out there, like the twin primes and things like that. There's questions that have been around for 300 or 400 years. Do you know what the twin primes are? The theory, it's like, if you do this, and just think about all the prime numbers, they occur in pairs eventually. Like you got 3, 5, 7. 3 and 5 are a twin prime. 5 and 7 is a twin prime. And then you go again, then you see 11 and 13. That's a twin prime. 17 and 19. Okay, 23 doesn't have a twin. Nor does 29 and 31 do. And then you start to see that the twins occur less frequently. Like 37 doesn't have a twin. 41 does. 47 doesn't. So they start, these twins, with primes that occur 2 in a row, they start to occur less frequently. And somebody, I should know this as a historian, so I'm going to admit some ignorance here, but I can't remember I don't even know who first conjectured it. Usually the names of people that first conjectured that are associated with the person are the wrong names. I'll give you an example of that today. But it's a question, it seems like a really simple question. Do twin primes always occur? And people have tried to answer this question for 300 or 400 years. I knew some Central students that I was working with a couple of years ago that thought they had the answer, and that's what they spent doing their class time in a differential equations course they were taking. The teacher knew they didn't, but they were working on it, and they had some good ideas. It turned out to be an idea that had happened, that somebody else had thought of like maybe 30 or 40 years ago, and I didn't have the heart to tell them, but they kind of figured that out. But it was a fun thing, and one of the guys still says he's going to do it someday, maybe he will. And so that's just a really simple math question. People have tried to answer that for 300 or 400 years. They haven't been able to. There was a big result recently about twin primes. I don't know if anybody knows about it, but they found out that a twin prime, the gap between 17 and 19 it's one number depending on how you count it. It's that even number. The gap between 23 and 29 would be 6. What they found out is the gaps between twin primes are no greater than 70 million. So if you have a prime, you know that if you go 70 million further, you're guaranteed to find another one. And then they've got it down somewhat. So this is no matter how far you go out. So these are really simple questions that people get intrigued by. To me, that's one of the really fun things about math, is you get simple things which are really hard to answer. You get hard things which can be easier to answer. But it's fun to try to figure this stuff out. So anyway, I like it. So I think STEM careers are great things to do. I think teaching's a great career. I don't know if any of you think about doing that. But you stay active. You get to meet interesting people. The way that society is constructed today, it's hard to get fired. Which you probably don't think about that stuff now, but as you get older, you do. You get interesting students. You get interesting adults you're working with. It's kind of a fun thing. You don't get rich, but you do pretty well. And depending on what you mean by pretty well. So. And then, just parenthetically, before I go into the talk, Gabriel said that there was some interest in Drake data analytics program, and if there is, I'd be happy to talk about that towards the end. And if you have any questions when I'm talking about anything, feel free to interrupt or ask a question, or if you don't understand something. Okay, I'm going to start, and I didn't bring a rush. I don't have a remote, but I'll just go over there if that's okay. But how many people here know about Pascal's triangle? It could be adults too, as well as, okay. Maybe it rings a bell somewhere that you knew it once and kind of forget it. Okay. And then how many people, again, adults or kids, I've asked you all if you've had calculus, but how many of the adults here have had calculus at some point in their lives? Okay. Do you remember what a series is? An infinite series? Okay. Do you, okay. It's like when you add an infinite number of numbers. I was looking to see if there was a board, but that's fine if there's not. I'll give you an example of one that's easy to figure out what it equals in a minute. So, what I'm going to talk about is something called a harmonic triangle. Has anybody ever heard of that? It's kind of a different, I think everybody should know, but I think it should be as famous as Pascal's triangle. And it's rooted in history, and so it has something to do with the birth of the calculus. So, this is Pascal's triangle, and it's obviously not in English. And this is from about 2nd century BC, which is about 1800 years before Pascal was born. So that's probably not the right name for it, or if it's the right name for it, it's not because he invented it. And I'm not quite sure why the Chinese were, it's a very interesting pattern, and I'm not sure if that was it. It's useful in solving equations. It's also useful in probability, but it's also just, it's one of these things, if you like numbers, and you discover it, it's a fun thing to play with. And I'll give it to you in a better way in a minute. This is Pascal's version, and again, to see the triangle, you can see it, but to see it the way it's usually written, you have to kind of look at it that way. You can see where the line is. That would be the way you'd have to orient yourself. And you can sort of see what the numbers are, but this is one of the ways that Pascal used it. And his interest was in probability, and he wasn't a gambler. But there is a sort of a famous question about what happens, let's say you're playing the best of 7, like the World Series or the Stanley Cup or something like that. Well, what happens if your game gets interrupted after only 4 games with no winner? What's the equitable way to sort of decide who's ahead? And using probability. And this was called the unfinished game. And there was a lot of phony theories about it. But Pascal and Fermat, who had another famous unsolved problem for a long time, they went back and forth to figure out how to answer that question, and they discovered a lot of the laws of probability. Which, I mean, if we do coin flips, we kind of know that if you flip a coin, 3 coins, there's 8 possibilities, or 4 coins, there's 16. It's 2 to the 4th, and we can write those out pretty quickly. But it seems that was not something that everybody kind of figured out on their own for whatever reasons. There's some cultural reasons, I think, for that. So it's useful in probability, solving equations. And this is the way we usually see it. Not quite with this way. This looks kind of like a game board or something with the counters. And you'll see why I highlighted. I didn't highlight that. I found that. But that's exactly the thing I want to highlight for later. But if you see how it's formed, you have the 1, and you have 1s all the way down the sign. And then if you add 1 plus 1, you get 2. And that gives you the 2 there. So you go to the 3rd row, which is 1, 3, 3, 1. Start with the 1, then you add 1 plus 2, and 3 is in the middle there. That's how you get the 3. And then you add 2 plus 1, and you get the 3. And then you go to the next row, 1, 4, 6, 4, and you start with the 1. You add 1 plus 3, and you get 4. 3 plus 3, and you get 6. And then 3 plus 1, you get 4, and so forth. And you can keep doing that. The 5 comes from 1 plus 4 above it. 4 plus 6 is 10, and so forth. So you could generate this as long as you wanted. And I think somebody told me, I don't know if this is the one or not, but somebody looked at, there's a mistake in there. And it's pretty easy to spot because it looks like somebody wrote a 5 instead of an 8 or something like that. But, oh, I see where, well, no, that's not it. I don't know. But somebody looked at that when I was giving this and said, oh, there's a mistake in there. So, and I don't know if anybody sees it. Okay, so we can come back to that. Okay, let me go back. Those numbers, does anybody recognize the highlighted numbers, 1, 3, 6, 10, 15, 21, 28. They're kind of faint. If you've, again, played with math patterns, these show up. Does anybody know what they are? You're shaking your head.
The triangular numbers.
Yeah, they're the triangular numbers. And I don't know if, where do they come up?
Triangles.
They come up in triangles, but 1 plus 2 is equal to 3. 1 plus 2 plus 3 is equal to 6. 1 plus 2 plus 3 plus 4 plus 5. I think I skipped one there. I'm losing track. 1 plus 2 plus 3 plus 4 is 10. It's 10. So these are also the sums of numbers. So if you sum the numbers 1 through 5, you get 15, and so forth. So you might have seen it come up in those kind of patterns. So, but here are the triangles. So you can see it better in the triangles. The first triangle number is 1, and then the second triangular number is 3. Those aren't minus signs. Those are just, I think, for emphasis. So you can see that if you write these triangles that way, it also happens to be the sum of the numbers. Okay. And so these are called triangular numbers, and they'll play a role. And then this is the sum of the triangular number, or this is the sum, the numbers you get. That didn't say that right, so ignore the topic there. But it's the sum of numbers. But you can. What I've done there is I've taken one triangular number and another and put them together to make a square. And this is a way to get the formula for the sum of the numbers 1 plus 2 plus 3 plus 4, etc. I don't have to go through all the details, but I kind of did here. So I want to sum the numbers. That summation means to sum the numbers all the way up to n, the whole numbers. And what I have there, I'm thinking that n is equal to 4, the yellow numbers. And so when I put the triangle with 4 with the triangle with 5, I get a triangle of 25, which is n plus 1 squared, 25. And that's equal to 2 times the sums of the yellows. But then if I sum 2 copies of the yellows, that leaves that last row of 5. So I can write the formula that way. And then what I can do is I can solve for that summation, and I can get a formula for the sum of the numbers 1 through n. Again, I'm not so much interested in the details. There's no test on it or anything like this. But what I'm trying to show is these numbers called the triangular numbers. They date back at least to Pythagoras in 500 BC, or probably before that. They sort of came about as sort of anecdotal history, which means gossip history, came about as it. Apparently the Pythagoreans liked to think about numbers and how they work together. They made a religion involving numbers. They thought everything was number. The whole world was composed of numbers. And so what they would do is they would sit around, they would play with little rocks and things like that and find number patterns. And there's triangular numbers, there's square numbers, there's pentagonal numbers, hexagonal numbers, and you can all get them from these patterns. But this is an example of triangular numbers. Okay. So I'm getting somewhere with all this. Okay, so this is a picture of Pascal. If you ever go to Versailles, you can see his picture there, along with some other famous mathematicians. And I figured the artist, even though he's long dead, deserves credit for their work. So I tried to find out who did this. This is Leibniz. Pascal was, let me go back to Pascal just for a second. He was a Frenchman that lived in the mid-1600s. He was very religious, and he was also a really brilliant mathematician. Besides the triangle that he used to figure out some probabilities, calculus didn't come about as we know it until the late 1600s, like things with integrals and derivatives. He figured out a lot of some basic ideas before that. He had a physical sort of adding machine, not just like an abacus, but something a little more complicated than that. He was very theoretical. He had sort of this tension in his life between math and studying theology. And he died pretty young. You can see he was just not even 40 yet. He got sick and died. But he was a brilliant mathematician, and he influenced a lot of other people. Okay. So, just again, a little bit of background. Sorry to keep walking back and forth and making it hard for you, but just a little bit of history. A quick, like 2-minute, 5-minute history of mathematics. A lot of the ideas in geometry go back to the Greeks and about, let's say, that was really between maybe 500 and 200 BC, so well over 2,000 years ago. And then other cultures, certainly the Islamic cultures in the 600s and 700s, the cultures of the East, China, especially in India, also had a lot of mathematical developments, but that didn't really reach the West too much until about 700, when some of the ideas came actually about 800, when some of the ideas came into the Islamic cultures. The Islamic cultures were between like 800 and 1,000, this is all AD, were sort of the height of the Western world in terms of culture and mathematics and things like that. And there was some communication with the mathematicians in the East to some degree. Not much happened in Europe until 14 or 1500, with some exceptions, and then around 1500 to 1600 with the Renaissance, a lot of big ideas in mathematics happened, like things like an equal sign, things like using a plus sign, things like using a decimal system. They hadn't thought of a decimal system before that. It was all what they call unit fractions. Things like, not even algebra yet. Algebra didn't happen until the early 1600s. So people would, if you had a word problem, they would write it out like it's spoken. So makes it much more difficult. It really wasn't what we would call trigonometry, even though those ideas were used like in astronomy and things like that. There's physics and astronomy. So it wasn't until the early 1600s that math came to start to look like the way that we recognize it in the West. And Descartes, about early 1600s, started using the notation that we use. Pascal followed him a little bit, but there was this explosion of ideas. At the same time, the Europeans were getting in touch with some of the mathematics of other cultures too. So there's an explosion of ideas. And so we went from algebra in the early 1600s to calculus in the late 1600s. And the people that were really behind sort of the development of calculus were Leibniz and Newton. And then Pascal was one of the people that laid the groundwork. So we go from Pascal, and then I'm putting Leibniz in there because that's who the talk is about. And he was a German diplomat, he was a philosopher, and he kind of stumbled upon mathematics on his own. And a lot of mathematicians in this time, in the 1600s, were self-taught. They didn't go to, again, parents don't want to hear this probably, but they didn't go to college. They didn't need to. They were able to figure out a lot of the stuff on their own, kind of like Bill Gates, and that kind of thing. So he was a diplomat. He did go to college. He wanted to be a philosopher. He wanted to figure out, through using algebra, to answer all life's questions. Like, what do I do? What day should we have the STEM talk? Let's make an equation we can work out through algebra and figure out the best. What's the right course of action to do today? And that was sort of this grand idea that he and some others had, is that we could kind of reduce all life's questions to algebra. But it didn't work. But he was self-taught. He was really interested in mathematics, and he wanted to learn more. And so in those days, what you did sometimes is you found, this is Isaac Newton, is you found famous I'll come back to him. You find famous mathematicians and ask them, can you teach me some things? Like maybe musicians do that. They find other musicians, they find master musicians today and say, can you teach me how to play the violin or something? So he went to Christian Huygens and said, I want you to teach me mathematics. And Christian Huygens says, yeah, I will, but you have to sum those numbers. Okay. I skipped over Newton, just sort of as a quick footnote, but he doesn't really enter the story, but he and Leibniz separately invented calculus almost around the same time. There's stories that they stole from one another, but that's not, they just have, the ideas were in the air, probably, and they kind of received them in a way. So Newton's just as important as Leibniz, but I'm not really talking about it. So Leibniz went to Huygens and said, if you can sum that infinite series, then I will. You can show that you're worthy, and I'll teach you. Anybody recognize what that series is? It's those. Yeah.
Yeah, it's the sum of the reciprocals
Yeah.
of the triangular numbers.
Yeah, so triangular numbers, and Huygens said sum the reciprocals of the triangular numbers. And again, you're adding infinitely many things, but not really, but that's for another time. But adding these kinds of series isn't really a dumb thing. For people who are already adding some of those, like there's a famous infinite series, and let me see. Let me use this. So, does everybody know what that equals?
2.
2. And how do you know it equals 2?
Formula.
Formula, right? Well, I was going to say that I'm going to give you at least one sort of intuitive reason. So I'm only going to worry about 1/2 plus 1/4 and so forth. And I'm going to try to show you that that's equal to 1. Okay, so I have a piece of paper here, and this is 1. This represents our unit of 1. So, oops, pretend I ripped this perfectly. What does that equal?
1.
That's 1/2. Okay, so that's the first term. We got the 1, so I'm at 1 1/2. Okay, how about this?
1/4.
1/4. Okay, let's see if I can line it up right. Probably already not, but we'll pretend. Okay, got 1/4 left. So I do this again. I got 1/8. I'm sorry, I told you. Okay, so 1/8, right? So I've added 1 plus 1/8. Take this off. What's half of this going to be?
1/16.
Okay. So you can probably see where this is going. I do it one more time. It's going to get too small. I get 1/32. So I can keep doing this forever, right? I'm always going to have another power of 1/2. And I'm always going to have a little bit left over, but I never get to the full piece of paper. That's summing all those fractions. And then so that gives me one full piece of paper, and then I have another one, so I have 2. The other way that I used to think about this when I was a kid is if I'm standing at that wall and I walk half the distance each step, do I ever reach that wall, at least in theory? No. And what you're doing is you're adding 1/2 of the distance plus 1/4 of the distance. You do half of that, that's 1/8 of the distance, 1/16. And I mean, I have big feet, so I'll hit the wall. Of course you hit the wall in real life, but in theory you never do. So adding that up equaling 2, it's a formula, but it's also, you can make it make some sense. And so asking to sum this is not absurd. That's what I'm trying to say here. In fact, the numbers are smaller in that one than this one, so it should add up to something. The question is what? Okay. So Leibniz thought about this and thought about this and thought about this. And he came up with this. This is the harmonic triangle. And remember how Pascal's was formed? It was addition. This is going to be subtraction. What you do is along each of the rows here, you put the reciprocals. 1/2, 1/3, 1/4, 1/5. And then so I look at the second row, and then I look at the third row, 1/3, 1/6, 1/2. So I go to 1/2, and 1/3 minus 1/6 is equal to what?
12.
I'm sorry, I did this wrong. 1/2 minus 1/3 is equal to what? 1/6. And then the other side I do the same thing. I subtract 1/3 from 1/2. So how about 1/4 minus 1/3? What do I get?
1/12.
1/12. How about 1/6 minus 1/12?
1/12.
I get the other 1/12. I'll do one more row, and so I'm looking at the 1/4. I take 1/4. I subtract 1/5. I get 1/20. This is probably a little bit harder, but I take 1/12. I subtract 1/20. You do the math. You do the arithmetic. You get 1/30. And so you can build up the whole triangle this way. So it's like a reverse Pascal's triangle using fractions. So he figured this out. I don't know if he did it on his own, but I don't know that it was around before him. It might have been, but I'm not aware of that. So he built this triangle, and I like to write it this way because it's going to be easier for our purposes. So what I did is, it's not just me that likes to write it that way. This is how I think it wasn't my idea. I just took all those and I shoved them all this way and lined them up. So I get 1, 1/2, 1/2, 1/3, 1/6, 1/3, and that's kind of what I did there. So I just realigned them. Each row is the same. Okay. So I just aligned them a little bit differently. And remember, he's trying to answer that challenge problem. So he was I think he was in his really early 20s around this time. Okay, so, and just to reiterate what I said before, the way I got the 1/2, which was the original column, I bolded it. I went to the 1/2, subtracted the 1/2 from 1. The way I get the 1/6, I go to the column before it. I take the 1/2, I subtract 1/3. And I go down for the next one. I keep doing that to get the 1/4, I take 1/3. I'm sorry. To get the 1/12, I subtract 1/4 from 1/3, 1/4 from 1/3, and so forth. It's been a long day. Okay, so I do that. I get the whole column right there, and then the next row, which if you went back, you would see was 1/3, 1/12, 1/30. Well, it shows you how I get it there. The details aren't that important, but it's just something that you can generate just on your own. You know, if you understand the construction, it's called a recursive process, and you kind of figure it out based on what's already there, and you can just generate this all the way as much as you want. Okay. And so remember, this is the goal that. Oh, wrong one. I know what I did. I hit the wrong one. So remember, this was the problem that and this is Leibniz's response. He was supposed to sum those numbers, and he said, okay. He said, I'm going to use my triangle. I'm going to go back to that triangle for a second. So to prepare you for what's the next phase, tell me if I add all the entries that are bolded and the boxed. If I add all those together, all the way down the line, what number do I get? So it's an infinite series. Imagine this thing goes down all the way. So start from the top. I add 1/2 to 1/6. What cancels? The minus 1/2 and the half. Okay. And then I add 1/2, 1/6, 1/12. So I'm adding all those pairs of numbers. The 1/2s cancel. The 1/3s cancel. I go down to the next row. What else cancels? The 1/4s. And I can keep doing that down. If I sum everything that's visible, I have 1 minus 1/8. Everything in between cancels. Now, those of you that had calculus, do you know what kind of series? Do you have a name for this series? This kind of series? We call it, in right teach, I call it a telescoping series, because you take something big and you compress it into something small. So what Leibniz said, if I form this triangle that way, and then I add that column, and I do it forever, kind of like what I was trying to illustrate here, what am I left with? Well, all I'm left with is that 1/2, 1/6, 1/12. But if you look about how I formed it, the 1/2 cancels, the 1/3 cancels, the 4ths, the 5ths, minus 6, 1/6, I get 1. So if I sum that first row there, I get 1. Okay. I mean, that second column. How about if I sum the third column? What do I get? It's the same principle. I get 1/2 because I get 1/2 minus 1/6 plus 1/6 minus 1/12. 1/6 cancels and the 1/12. So I'm just left with that first number. And so again, Leibniz invented this. He had one problem and he said, this is my answer. So this is how he answered it. This will hopefully make more sense. He was supposed to sum those. He looked at his triangle and said, okay, well that's what my first column, the second column is equal to. Just what I went through. And then you break up the 1/2, the 1/12, the way that he did. And then you look at it right there, and he said, okay, well that number, the sum of the reciprocals of the triangular numbers is equal to 2 times my column. And then he said, okay, I'm going to add my column. So he broke it up, and then he rearranged the terms, and you can see the cancellations. And so if you do that all the way down the line, it's like, you know, knocking down a row of dominoes. All you're left with is the first thing, the 1. And so he said, okay, I do all that. Everything cancels but the 1, so the answer is 2. So he says that sum up the top, your challenge problem, it equals 2. And so that's what he used the harmonic triangle for. And what I find, I'm going to go back to that triangle for a second, and maybe I'll go. That way it's maybe a little bit easier to look at, I don't know. But he had a simple problem. And which column did he need? He only needed the first 2 columns. But then this is how a good mathematician thinks. He says, okay, I'm going to solve this problem but I'm not just going to solve this problem. I'm going to invent a method that solves all kinds of other problems. So he didn't solve one problem. He solved infinitely many problems. And again, that's one of the things. A scientist does the same things. I think that's one of the things that happens in the STEM world, is you look at a problem and you develop some kind of scientific approach to it. You realize that your approach to this problem can solve all these other things as well. And then you get optimistic, irrational exuberance. And you say, okay, he said, I can solve he said, I can add up any sum. This is what he's reported to say. He may not have actually said this. He said, I can use this triangle, and this is actually a calculating device. It's not a machine, but it's a table of calculating sums of series. And you can, like I said, you can sum infinitely many series with this. And he said, I can sum every series there is with this. And evidently not. But he got so excited by his thing. He said, I'm not just summing this one series, I'm summing every possible series. And again, this is somebody who wanted to develop a symbolic language to answer all the questions of the world. So of course, I mean, it's the other, we overreach sometimes too. I mean, especially, I think people in STEM and science and math can get really excited and think they've really answered, the key to the universe, and they've done something pretty astounding, but maybe not quite, solving all the problems in the world. So that's kind of why I like this triangle, because it's a really deep thing, and it's a perfect kind of problem-solving approach. You're solving a lot of problems, and you're inventing this wonderful thing. And if you're a mathematician, it's beautiful and it's fun. Now, I would have a hard time explaining that to some people I know in my family. That how much fun and how beautiful that is. But I think it is. I think it's pretty remarkable. So I'm going to leave you with a problem, and I can't decide whether I want to give you the answer or not. Do you want the answer?
Yeah.
Okay. You see that Gabriel, I'll email you this triangle so you can use it. But okay, that's the sum of that's the slant row of the Pascal's triangle. That slant, if I look at those as reciprocals, it's the reciprocals of the numbers, of the triangular numbers. What I want to do is I want to sum the reciprocal of the next slant column. Not the one that I've highlighted, but the one next to it. 1 plus 1/4 plus 1/10 plus 1/20 plus 1/35, and so forth. And you can use that triangle to do it. And the technique is really similar to what he did to find that sum. And I'll leave it to you to do it. It's not, once you get the trick, it's not that hard, but it's difficult to see easy things sometimes. At least I have that problem. You can Google it if you want. I mean, but try to solve it, and I'll send you that stuff. I don't know if we have Wi-Fi here, but I can do it before I leave or something like that. And see if you can figure it out. And again, you can use that triangle to do it. Okay. So anyway, I just think this should be as famous. I mean, the harmonic triangle should be as famous as Pascal's triangle. I think it's just as cool, just as interesting. It's kind of not known. And I'll close by saying that this got Leibniz thinking. He hadn't invented the calculus yet. But he started to think about, I can add up really small things, really tiny changes, what's called infinitesimal. And it's like I can take something that's whole and I can find its infinitesimal components, and then I can use that for other things. And so he started thinking about like taking an interval and you break it up into dx's, delta x's, if you've done those limit problems. And it started to think about, well, there's rules for how I divide things up, and there's rules for summing these small things. And so he kind of realized, well, that's integration. And so he developed a system for integrating and taking differentials. And a lot of it had to do with the fact that he spent so much time working on that triangle that it got him thinking about other things. And it got him engaged and started thinking about these questions he didn't anticipate. So I think another thing that happens with math, with STEM, with science, with English as well, is that you start looking at one problem and you solve it and you do a great solution, and then you your mind doesn't stop working, it keeps churning. And then you start discovering other things that are unrelated. You're thinking about one thing, but suddenly you're thinking about something else, and you get this insight. So, to me, it's not only a beautiful triangle, but it really had this role in the development of the calculus. So, anyway, that's it. So I enjoyed giving this talk. So, thanks for listening. So I'd be happy to answer questions. I know when one of my colleagues was here, he said he got questions about like why is college so expensive or stuff like that. So I thought about that. I have a good answer for that, but you know, so if you have questions about, I mean, Gabriel suggested you might have, there's some interest in, Drake has a new program in data analytics, big data, and that there was some interest in that, so I can talk a little bit about that, or if you have questions about the math. Or other things, you know, I don't know, Barton? No, yeah, go ahead.
I'm curious about the math, but also the data analytics. I think that would be interesting to hear from you about what's happening with that at Drake.
Okay, and I have, if anybody's interested after you go, I have some material about that if you want, but you don't feel you have to take it or anything like that. But that's what I ripped up. That was one that was all kind of messed up. But so I figured I'd use it. But how many people here program? A little bit, you know, Java or whatever language you use, you know, and then people, have you looked at statistics at all? Okay, so I don't know if you know what a database is. Just a way to store information that you need. You can look at that as a database of coefficients for binomial expansions if you know math. You can look at this triangle, whichever version you like, as a database of series. It's encoded in there in a certain way. And the question is, well, how do you dig out that information? Now Leibniz, this particular database, Leibniz created it, so he knew how to manipulate it and to draw things out. And I was trying to teach you how to access this database of information in a particular way, or trying to show you how to do it. And so the world, first of all, there's computer databases that have like where you click on the web, where you know, if you have a credit card, you know, every cent you spend, what magazines you subscribe to. Are there sports fans here? And I don't know, has anybody ever seen Moneyball? Yeah. Moneyball is like one of the best examples of data analytics I can think of, because what Billy Beane and the Oakland A's did, now every baseball team does that, so in basketball, not so much in football, is there's so much information in sports that was never used. People store what's happened before in baseball, they keep statistics, and then Billy Beane hired some mathematicians and our computer scientists, both statisticians, kind of all the same as far as I'm concerned, and said, like, what correlates to winning a baseball game? And so people dove into the data and figured out things like, well, obviously runs, but what produces runs? Well, walks is one of the things. Walks are really, I kind of like walks, because that's where I was taught to have a good eye in baseball when I played, and I thought a walk was a good way to get on base. But it's not very, you got to wait, it's patient, not much action. So walk was not a valued commodity, but Billy Beane, through looking at the statistics, realized that there was an inefficiency in the marketplace, that walks came cheap, walks helped teams win, so if you could find someone that walked a lot, you didn't have to pay a lot of money for it. And so you had a competitive advantage. And so he developed that, and so other teams followed suit. So that's an example of data analytics. You're looking at existing data, you're using analytical tools, and you're coming away with maybe some insights that people didn't have before. Insurance companies do this. It seems an obvious thing when you realize it, but they found out that one of the best predictors to being is your credit score. So if your credit score is high, you're probably really good insurance risk from the company's point of view. And again, that seems obvious when you think about it, but the statistics weren't really showing that up. And then other examples, Twitter feeds, that's a huge database of all the Twitter feeds. There's one thing I read that outbreaks show up in Twitters before they show up in hospitals, because people talk about their symptoms. And if you read them the right way, you can see, okay, there's this flu outbreak coming. I just heard another thing on the radio a couple of weeks ago about that if you have a community and there's certainly, you've developed a way to measure anger, if the anger is too high, that community it correlates to the community's heart risk, or lack of heart health, so the coronary risk. And so again, who would have known that? People look in the data and they figure it out. So the way I look at data analytics is that basically everything's a database. I mean, the world, baseball, basketball, Twitter feeds, images, everything you do on the web. And to understand, you want to understand that data, you have to develop tools. Now, we had statistical tools, but those aren't up for the task. Another issue is that some of these data sets are so vast. Like I have a friend that works, he might be a good person for this. He works at Pioneer and has a lab. And a few years ago, he was working on he was collecting all these gene informations of the human, not the human genome, but probably plant. Vast amounts of data, but didn't know how to access it. It just took too long for a computer to figure it out. So first of all, you have like sets of data that don't give up information by traditional statistics. You have data sets which aren't traditional, they're not zeros and ones necessary. There could be a Twitter feed or something like that. And then you have data sets which are huge. And if you do the math, it could take like, I don't know if you've ever, I don't know, there's things that a computer could spend like centuries doing and not crack. Like if you have the right RSA encryption, for example. And so people have developed new techniques to look at data. It's kind of a completely open subject, meaning that the answers aren't all there yet. If you study calculus, the answers are there. It's in higher math where they're not. But so data analytics is sort of I like to call it data science. It's the science of how to use data to make decisions, or to understand things, or to improve the world, or to get better ad clicks, or however you want to use it. It's got good and bad uses. And so it's just sort of coalesced in the last few years as a subject. Sometimes it's called big data. And so Drake has a program, and it's going online this fall, and basically it's a mixture of computer science, mathematics, statistics, and the idea is to train data scientists. And the thing that parents might like, and I've tried, my daughter majored in computer science, I said, you really should look into this data analytics stuff, but she didn't, is that there's going to be a huge shortfall in jobs. Like I saw an email to our Drake president from, I can't remember which company, but he said if we can hire 3 data analytics students a year from Drake, we can save our complete job search budget or something like that. So a lot of the local companies are seeing Drake and other schools as a way is to look at these data scientists and to grab them early. And so there's a lot of opportunity for employment. I think there's a lot of opportunity because it's a vast number of unsolved problems that are out there. The techniques haven't been developed yet. And so what Drake and other schools are trying to do is just to develop a core set of skills. And our approach at Drake is, let's say that you like, Drake's famous for actuarial science, so you want to become an actuary. Well, we develop a track in data analytics for actuary. You like computer science, working with databases or whatever in computer science, well, we have a track in data analytics for computer science. There's one for mathematics. Modeling is another big thing. You want to figure out how a process in the world works. You want to study it. One way is to look at it mathematically, which is what's called a black art. Again, there's not set answers to these questions. And so so whatever tools you used are legal tools. So there's a whole vast number of things that it's used for. So it's brand new. I'm kind of excited by it. It doesn't sound that sexy, but like I think if you like computers, you like math, you like solving problems, I think it's really good opportunity. Like I say, I tried to convince my daughter to kind of look into it and stuff like that. But she's more interested in other things with computers. So that's a quick overview about that. And I'll be happy to talk about it more too. Okay. So professors give long answers to simple questions. So. Okay. Oh yeah, Gabriel, yeah.
This is more about the math. Is there a way to define what specific series could be summed by the Leibniz triangle?
When I said that, every time I talk about this, I wonder about that. And there's issues where you look about what kind of techniques can solve problems. It's more of a computer science issue, but it's just sort of the studies of complexity. I mean, there's math in there too. I don't know the answer, but I was wondering how one would. When I said that today, I was wondering how one would solve that question. Because you add. I don't know. I don't know. I mean, because you're adding rational numbers, so I don't know if you can add rational numbers and get irrational numbers, but it has an infinite number. So, but the fact that you can reduce them to telescoping, that must really limit the sort of series that you can solve. So I don't know. I mean, I think that's a really interesting question. Okay, well, thanks a lot. I enjoyed this, so thanks for coming.